The goal with this lesson is just to further develop the whole, benefit of knowing the tangent lines for a curve. You know, how you basically find a tangent line is you take your equation of your curve, you take the derivative of it, you evaluate at a specific point, and at least that's the slope of the curve at that point, and it's also the slope of the tangent line at that exact point for the curve. Okay, and the key that with this whole first part of this lesson is to focus on this main equation right here, that the linearization, which is just basically a tangent line used to estimate what your graph is doing at a specific point, is evaluated by finding, first of all, the function evaluated at a specific x value plus the derivative times x minus a. So it's just, like I said right over here, all it is a manipulation of your point slope form, where you just move the y1 over to the right, because the derivative evaluated at a is your slope, x minus a, and this is just y1 right there. Okay, so let's look into our first example. We want to find the linearization of the function f of x is equal to the square root of x plus 9 at x equals, or at a equals negative 4. Okay, so to get started, to find the linearization, let's just write out that formula. So the linearization of x is going to equal the function evaluated at a plus the derivative evaluated at a times x minus a. Okay, so first of all, let's find f of a. F of a is going to be the square root of negative 4 squared, so 16 plus 9, which is 25, so the square root of 25 is 5. So f of a is 5. Let's go through and find the derivative. Well, I know that f of x is really x squared plus 9 to the 1/2 power. So f prime of x is going to be 1/2 times x squared plus 9 times to the negative 1/2, and then times the derivative of the base, which is 2x. And if we clean that up, then f prime of x is going to equal to 1/2, so of 2 is 1, so x times x squared plus 9 to the negative 1/2. Okay. What we also have to find is now the derivative evaluated at a, so the derivative evaluated at negative 4. F prime of negative 4 is going to equal negative 4 times 16 plus 9 to the negative 1/2 power. So that's negative 4, and it's going to be 16 plus 9 is 25. 25 to the negative 1/2 power is basically saying the square root of 1/25. So that is 1/5. So negative 4/5. And if we put all this information together into our one main equation, then our linearization of this function is going to be 5 minus 4/5 times x minus a, x minus a negative 4, or x plus 4. And if they want us to finish just kind of combining like terms, you'll get negative 4/5 x minus 16/5 plus 5, and then to finish this up, so negative 4/5 x plus 9/5. And there, right there, is a line, pretty much it's the tangent line, that can be specifically equation for the tangent line at a equals negative 4. Alright, let's go down and finish looking here at number 2, example 2. So let's do this process again. The linearization of this new function at x equals negative 8. So first of all, I think of, okay, that's really x to the 1/3 power. Okay. And the linearization, L of x, is equal to f of a plus f prime of a times x minus a. All right. First of all, let's find f of a. So f of negative 8 is going to equal negative 8 to the 1/3 power, or the cube root of negative 8, which is negative 2. And then if we go through and find the derivative of x, it's going to be 1/3 x to the negative 2/3. Okay? Or if we want to think of it like this, it's 1 over 3, and then it's the cube root of x, all of that squared. If we want to put it in that form, if that's going to help us solve this out for the next part. So then the derivative evaluated at our a value going to be 1 over 3 cube root of negative 8, all of that squared. So 1/3. The cube root of negative 8 is negative 2 squared. So 1 over 3 times 4 is 1/12. Okay, so putting this into our formula, then we have the linearization function to be negative 2 plus 1/12 times x minus a negative 8, so x plus 8. And cleaning this up a little bit more, we have 1/12 x, 8/12 plus minus 2 will give us a negative 4/3. And there's the linearization for that function specifically evaluated at a equals negative 8. Okay, so hopefully so far not so bad. And let's just keep on going on. Example 3. We want to find the linearization of the function 1 plus x at an integer close to x naught equal 8.1. Okay, remember integers is something you can count on your hands. And so I'm thinking what would be close to that would obviously be x equals 8. And so that's what we're going to estimate it. Or if we kind of use the terms they've been doing before, it would be a equals 8. All right, so linearization. Do you want me to write the formula again? L of x is equal to your function evaluated at our a value plus our derivative evaluated at a times x minus a. Okay, so first of all, our function evaluated at our a value, which I'm picking to be 8. To me, that's the closest integer to 8.1. And that's going to be 1 plus 8 is 9. Then we're going to take our derivative of our function. The derivative is 1. And so if I take the derivative and evaluate that at 8, then obviously it's still going to be 1 because there's no value to plug it into. So coming over here to the linearization process, then L of x, it's going to be f of a, which is 9, plus 1 times x minus 8. So the linearization for this function is going to be x plus 1. So again, what we're finding is just an equation for the line that is a really good estimate of exactly what, if I wanted to look at this main graph, what this main graph is doing specifically at the point 8. This is what this linearization is really finding for us. And what I mean by what the graph is doing, specifically the shape of the graph, the slope of the graph. Okay?